We are now recording. All right, cool. So reminder, everyone, homework 8 is due today at midnight. I have a homework party after this if you want to come and if you're having issues. So just follow me after class. If you're having issues uploading your zip file, Replit changed some stuff. So they are downloading like a ton of folders for some reason, like some cache folders, etc. The autograder only needs these 3 files if you're doing C++. So if you want to like manually download those 3 files to your computer and then upload those 3 files to Gradescope, that will definitely work if you're having issues uploading it. If you're trying the .zip method, it seems that if you recently ran the program, it just has a bunch of other crap on it. And when you upload it, Gradescope gets unhappy. It just doesn't know how to deal with like thousands of files. Yeah. Makes sense for the core class here. Also, in case you guys don't know, my manager is going to be watching this lecture, so ask a lot of questions. No, like on Zoom. They're not here. Okay, moving on. Homework 9 is out. This is going to be due next Wednesday at midnight. I do know Friday is a holiday, so I made it a little shorter. Yeah, and I heard Monday is a mental health day, so I made it a little shorter. So it's a little shorter, but it is not a lot shorter, just a little shorter. Okay, so you will still have to do some work. And this is on greedy algorithms. So I actually think it'll be really fulfilling for you guys to do them because, like I said, greedy algorithms are usually not too hard to think of. It's usually like, is this the right algorithm that is really like the complicated, difficult part? But thinking of the greedy ones, you should always be like, what is the dumbest thing I could do right now? Like not the dumbest, but like what is the easiest thing I could do? Cool. End of semester course evaluations, our goal is 80%. I'll skip this part. And now we're gonna finish covering up Kruskal. All right, come on guys, let's quiet down. Yeah, pay attention, okay. Okay, so the plan for today is we are going to review minimal spanning trees. So I need you guys to be able to define and identify a minimal spanning tree. So if I give you an example, the goal is for you to be able to explain why minimal spanning trees are useful, okay? Then we're gonna introduce Kruskal's algorithm. So last lecture, we covered Prim's algorithm to find minimal spanning trees. This time we're gonna introduce Kruskal's algorithm and we're gonna compare it to Prim's algorithm, okay? And then lastly, we're gonna introduce, if we have time, we're gonna introduce this idea of maximum flow. So both minimal spanning tree and maximum flow are actually really practical algorithms that are used. And I've got like a pretty interesting story to tell. So we're going to start with this. Oh yeah, also FYI, we are going to be skipping a few proofs, but they're in the lecture notes if you're interested. You are not responsible for stuff that's not on the lecture slides. Just FYI. Cool. So this is the example from last lecture. We have an undirected weighted graph. A spanning tree is a tree that connects all the vertices, right? Spanning means that you're connecting everything. You guys should, this is a review, you should remember from last lecture. What's a minimal spanning tree? Jonathan? Yeah, the lowest total weight. So you can define the weight of a tree as the sum of the weights of each edge that's in the tree. And then the minimal spanning tree is a spanning tree that has the minimum weight, right? So again, it should not, like this is the minimal spanning tree for this graph. It has cost 37. There are other minimal spanning trees that have the same cost. There are other spanning trees that have higher cost, okay? And these are actually really important. So I didn't emphasize this enough last lecture, but minimal spanning trees are used in a lot of places, like to figure out how to design networks, to figure out how to design, like how to lay out telephone poles, telephone connections, how to lay out like electricity, roads, etc. Because they do, in a sense, they tell you like what is the minimum cost you can use to connect everything, right? So everything is connected. So electricity, if you have a minimal spanning tree, that means every node is getting electricity, but it is taking the minimum amount of cost to like build those electrical lines, for example, right? They are also used a lot in genetic distance. So I'm not too familiar with this, but I am familiar with the image processing. So image segmentation is the idea of taking a picture and trying to segment it into different regions. Minimal spanning trees are actually used to do that.
Like you say regions, like lower third.
Oh, no. Like the region containing dog, like if there's several dogs. So like it's a mixture of object detection and image segmentation is where like all these pixels belong to a dog and all these pixels belong to like the background or something. Yeah. Okay. So hopefully you guys remember Prim's algorithm. Who remembers how that algorithm works? Like we covered it last lecture. David? Yep. Yeah, so Prim's algorithm is very straightforward. You start with some vertex. It doesn't matter which one. You start with some vertex and you say, what is the cheapest way I can connect this vertex to something in the rest of the graph? Yeah. More similar to Dijkstra's algorithm. It is a little similar to breadth first search in that we're considering neighbors of the vertex, but we are also considering like other connections we might have, right? So we actually have to keep track of like, so let me grab my markers. That actually I left my markers in my office. Okay, so no marker, but you can imagine like if you already have these nodes connected, or like let's say this one, like these are already connected, then you actually have to like keep track of all the edges going out of that set of nodes, not just the neighbor, right? But it is exactly Dijkstra's algorithm. You just have to you change the update function. Yeah. But Prim's is not the only greedy algorithm. There's actually one that I personally think is easier to implement and easier to think about. Oh, thank you. I appreciate it. I will give this back to you. Yeah. So what is another greedy algorithm? You guys actually came up with this last lecture. What's the other greedy algorithm? Jonathan? Yeah. Yes. So the other greedy algorithm is take the cheapest edge that does not create a cycle, right? So here you would take edge 1. What's the next cheapest edge that does not create a cycle? There's, yeah, question? Or 2? Yes, it is 2. You could take either one. Either of these is valid. It'll give you a correct answer. It doesn't matter which one you take. It just has to be the next cheapest that does not create a cycle. What's next? The other 2? Great. What's next? David? 4. I took this 4, but there's another 4. Either one would have worked because they don't create a cycle. What's next? The other 4. Great. What's next?
7.
Which 7? This one, it actually matters. Yes. If you take this 7, that creates a cycle, which is not a tree anymore. So you shouldn't do that. You have to take this 7. But yeah, you're right. It is 7. Or actually, it's not 7. Sorry. So the next you should have thought about is 6, but that creates a cycle. So you don't take it. Then you think of 7, but this 7 creates a cycle, so you don't take that one, right? What's after this 7? Which 8? Does it matter? It doesn't. Either one works, but let's take that one because it doesn't create a cycle, right? What's next? Yeah, question, Jonathan.
Wouldn't it create a cycle if you took A? If you took the other B, because you go H A B, or you go E A.
So a cycle means that you can go back to the node without crossing the same edge. I don't think this. Yeah, I don't think this creates a cycle. Yeah, question. Oh, you cannot do both 8s. Yeah, both 8s you definitely cannot do, but you can do either one and then continue. Yeah.
So if there's if there are 2 weighted edges, they're the same, like, they don't create a cycle.
You will end up doing both, but the way to think about it is you only ever add one edge at a time, okay? And in this case, you could do either one. And then what'll happen is we'll add this 8, and you'll be like, well, what's the next lowest weight? And you'll think, oh, maybe I can add this 8, but you cannot because now it creates a cycle. So the logic is just go in order, and then if you can add it without creating a cycle, you take it. If you cannot add it without creating a cycle, you don't take it. Cool. So the next one is this 9. What's next? Somebody said it's done. Yeah, how do you know it's done?
Because any other edge would be cycle.
What's another easier way to know it's done?
You have it -1.
You have n-1 edges, right? So I don't even need to check that adding other edges will or will not create a cycle. When I get to n-1, if I have been following this process, I will have a spanning tree. So it'll be done. Cool.
So I have a quick question. In
Yeah.
the actual implementation of this, like for searching each one, is that taking constant time?
Yeah, we're about, there is a way to do it that takes constant time. We're going to talk about it, but a naive implementation of this would be slow. And we're actually going to talk about it. Yeah. So what you guys just described is actually called Kruskal's algorithm. So this was discovered in the 1970s, I believe, by Kruskal and a bunch of other people. But we use his name for some reason. And this is the algorithm. So this is the slow one where that is not optimized yet. The very first thing we do is we sort all the edges, right? So you want to process the edges from smallest to biggest. So you sort them, right? So you have a way to keep track of the weight of to go from a weight of an edge back to the edge itself, right? Then you create your MST, which is going to be a collection of edges. So this is like a unordered set or just a set or an array or whatever you want, right? And then for each edge in E, so you iterate over your sorted edges. If adding the edge E to the MST won't cause a cycle, so this is what we were talking about, if it will not cause a cycle, and in your head, you should be like, well, how would I implement this? That's something you want to think about. But pseudocode would be if it won't cause a cycle, then I can add E to my MST. So I added. And then when I'm done, I return the MST. And that's it. That is the entire algorithm. Creates a minimal spanning tree. This is the pseudocode. Any ideas on running time? And again, there's going to be stuff that I haven't told you how it's implemented. So you might have to like leave it open-ended to be like, oh, it depends. How long does that take?
Yeah. Like,
Yeah, Leander, back there, you want to get started? The sorting. Okay, so yeah, so step 1 is you sort. What's the running time of that? So you're sorting the edges. How many edges do we have? M edges, right? So sorting all the edges is going to take you at least, we know, no matter how you implement it, we know it'll take you at least m log n if you know nothing else about the edges. Okay. In practice, most edges are integers. Most graphs have integer edge weights. Most graphs have a maximum edge weight. So could you do this faster in practice? So this is like if you know nothing about the edge weights, it could be anything. You're just trying to compare them and you're trying to sort them. Yeah, Leander. Yeah. Yeah. So if we know the highest one, and let's say the highest one is like 1,000, we could do bucket sort or radix sort. And those have running time O of M because there's M edges. Right? So you do have a few options here. So in general, this is M log N for, and why is this N, by the way, instead of M? Or why does it not matter? Yeah, because if you have log M, M is at most N squared. And by the rule of logs, that's 2 log N. And by big O, the two doesn't matter. So they're actually the same. So yeah. So again, but again, you don't need to know that. If you put log m, that's fine. It's also correct. Same thing. But either you can sort the edges, or you can sort them using radix sort or counting sort, which is going to be O of m. What about the next steps? Who wants to finish walking the running time for this? So how long is this for loop going to take? O of m, I'm just going over the edges, right? So the for loop by itself is going to be at least O of m, and then I'm doing something inside of it. Yeah. Yeah. So this if statement, you guys should be asking, how do I do this? Do you guys have any ideas like how you might do this, even if it's not fast? What is the fastest you can think of doing this? It will not cost a cycle. Yeah.
Like you can store the nodes that you visited, so if you reach out that you visited, then now make a cycle.
If you reach a node that you visited, that would make a cycle. Yes, that is a good idea. How long would that take to run? You don't have to do it doesn't have to be a smart way of checking this. I'm just trying to get if you just had to implement it right now, knowing what you know, how would you check that? Let's say I have all the visited nodes and then I'm about to add an edge. And how long would it take me to figure out whether I visited or not? Yeah.
Maybe use an order map because
Use an unordered map because it will not add another key value if you already have that key. That sort of works, but not always. I just want don't try to be clever. Just give me what's a dumb if you're checking for this cycle, what is is it gonna be n cubed? Let's say, is it gonna be that bad, or is there just yeah. Yeah. So I think both of you are kind of getting at this. So in the worst case, you guys should be able to run DFS, for example. So consider the graph that you're creating, add the edge to it that you want to add, and then run DFS. If you came back to a node you've already visited, it has a cycle, right? So at worst, so naively, there are many algorithms you can use. This would be O of n plus m. Okay. Now, what is the total running time then? Yeah, Leander. So this is a for loop. So this will be m times m. So it'll be m squared. The n is actually smaller, so we can forget about it. And then this is actually smaller than m squared. So the running time is just O of m squared. Okay, which is really bad because that can be O of n fourth, right? So that's not good. Also, you guys can forget this till conversation, does not matter. It turns out that we're going to talk about this first. There is a way to implement this so that you can check for cycles in constant time, which means that the running time is going to be dominated by the sort. And if you can sort quickly, like in linear time, then the whole algorithm is linear time in the number of edges. Cool. So one thing to notice is that at each step of Kruskal, we are maintaining a forest of possible candidate trees. So what does that mean? That's what this looks like. So Kruskal is not always connected, right? So prims is always connected. We start somewhere and we grow the tree from where we started. Kruskal takes random edges from wherever, right? So at any point in time, we're going to have some set of connected nodes that are not necessarily connected to each other. So if you're connected to each other, you create one forest. If you're disconnected, you're another forest, or you're another tree. So we call it a forest because there's many trees, right? So when we add an edge, what actually happens is we end up merging two trees, right? Because now if all of these are connected and all of these are connected, when we connect the two trees, that creates one big connected tree, right? That makes sense? This is just introducing a little bit of terminology. Okay. So what we want to do is we never want to add an edge that's within the same tree, right? Because if I add an edge between I and G, that edge is within the same tree. So that creates a cycle. So that's what we're trying to avoid. Okay. It turns out that you can do this with a special data structure. It is not called a tree house, but I think they should call it a tree house. It has a better name. It's called a disjoint set data structure. We are not going to cover this data structure in detail. I am just going to tell you its API and how fast it is. If you want to learn how to implement this data structure, Wikipedia. This is such a rare data structure that it does not come standard in like C++. You'd have to implement it yourself. Okay, so it's not a very common data structure, but you need it for this algorithm. So what it lets you do is it lets you store a collection of sets, so a set of sets, and it supports the following operations. Make set, which takes in an element and creates a set out of it. Okay, so it takes in something and it creates a set out of it. Find U, which takes in an element and it tells you what set U is in. So for any element, it'll tell you what set do I belong to. So you can create sets. You can find which set elements are in out of all the sets you've created. And the other thing it supports, it lets you union two sets. So you can take a set that has element U and a set that has element V, and it lets you combine them into a bigger set that now has all the elements from both U and V. Okay, those are the three operations. Does that make sense? Yeah. So here's an example. So let's say I say make set X, make set Y, make set Z. Those are the function calls I'm calling. I'm just passing it in some X, Y, Z, some numbers, let's say. And then I union X, Y. So somewhere in the back end, what this data structure is promising you is it's going to make a set out of X. It's going to make a set out of Y. So that's this line. Make set X, makes a set. Make set Y, makes a set. Okay. It's going to make a set out of Z. And then when you call union XY, it is going to combine these two sets. Okay. Something like this. Then when you call find X, it is going to return you this set. So when you call find X or find Y, they're going to return the same thing because now they are in the same set. Okay. This is the data structure. Can you guys see how this might be helpful for Kruskal's algorithm? If I gave you this data structure that does this, how would you implement Kruskal's algorithm? Yeah. 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 So to start out with, yeah, Serena. It will do nothing. If they're already in a set, then it'll do nothing because they're already together in the same set. Yeah. But yeah, generally you probably don't want to call union on. I mean, you can if you want to. It turns out all these operations are O of 1. There's a data structure that supports them in constant time, all three, right? So it doesn't matter. But good question. Yeah. So you're right. So the first thing would be I'd create a set out of every node, and then I'm iterating over my edges. I see the first edge. That's going to give me 2 nodes. And what functions would I call here? Like, what does my pseudocode look like? So I give you these functions. You don't have to implement them. They already exist, right? Yeah, Leander? Yes. So every edge you process is going to connect 2 nodes. You will call find U on one node, find V on the other node. If it returns the same set, then you skip that edge. right? Because they're already in the same tree. Otherwise, what do? If they're not on the same tree, you union U and V, right? And that's it. That is the pseudocode. So if I gave you these functions, this is the pseudocode for Kruskal. And I claim, so I'm not going to teach you why this works. It's not that complicated, but it's not a trivial data structure to analyze why it runs. They actually don't run in constant time, but for all intents and purposes, they're basically O of 1 functions, okay? So what is the running time of Kruskal? So let's assume these functions are all O of 1. So find is O of 1, make set is O of 1, union is O of 1. What is the running time of Kruskals in that case? Somebody that's not Leander. Maybe somebody on Zoom. David? Yeah. O of M. Yes. So this part is O of N, and make set is going to be O of 1, right? This part is O of M because I have to iterate over all the edges. Find is going to be O1, O1. Adding to the MST is just adding to a set or adding to a vector. So this is going to be O of 1. Unioning is going to be O of 1. So this whole thing is O of M. Sorting the edges by weight is either M log n, or it could be O of M as well. If you know that your maximum edge is like 1,000 and you use bucket sort, right? So in practice, Kruskal's algorithm could be linear, right? In practice, linear in the number of edges. So again, once more, this is what we do. To start out, we create a set out of every single node. So now every single node is in a set. We consider the smallest edge. So in this case, we're going to consider edge 1. We're going to call find on H and find on G. It's going to return 2 different things because they're in different sets. So we're going to say, let me union you two, right? So we union them together. What's the next edge I consider? Same example. We consider one of these two. So either this one or this one. I forget which one I did. I think this one. I think I did this one. So it's going to call find on G, which is going to say, I'm in this set, whatever name that's called. And then it's going to call find on F, which is a different set. So it will, again, take that edge and union. And I was wrong. We actually took this edge. Okay, so I forgot which one we did. So we did that one. What's the next edge we would consider? The other two. That will union that way. So you can see the sets, the sets that we're considering in our data structure are getting bigger, right? What's next? Take the 4. So it'll call find on C, and it'll say, here's one set. It'll call find on F, and it'll say, well, F belongs to this different set. So they're different, therefore I'll union them. Oh my God, I did this 4. But then the other 4, okay? Great. What's next? One of the, oh, the 7, right? Yeah, the 7 over there, right? But you will notice, so the other thing is like, I am skipping a few steps, which is, it'll consider this 6, but it'll call find on I, and that will return, like I belong to this set, whatever you want to call it, like set 5. And then find on G will also say like, oh, I belong to set 5. So they're the same, therefore we'll just skip over that edge. We will not add it to our MST. But if you continue, then eventually you union everything, you get your MST. Now everything belongs to the same set and you're done. Cool. Like we said, running time, sorting the edges, you guys told me this, so I'm just summarizing, takes M log n. In practice, like we said, if the weights are small, you can actually sort it in O of M time. See, you guys should have written the slides for me because you came up with all of this. For the rest of it, you have n calls to make set. You have 2 m calls to find, which is O of M, like you guys said. You have n minus 1 calls to union, which is O of n. And then the total running time is m log n, because actually the sorting is the one that takes the longest. But it's a little bit closer to O of M in practice, because usually you'll use radix sort for this type of stuff. Okay. So I did lie to you guys a little bit. So technically, the running time of these functions, make, set, find, and union, is amortized over all of the operations. What does that mean? That means that sometimes it's constant, sometimes it takes a really long time. On average, the running time is not constant. It is the inverse Ackermann function of n. If you guys have heard of that function before, you must be doing some pretty heavy duty math. Anybody heard of that before? Inverse Ackermann. Oh, Jonathan. Okay, so the one when I first ran into this data structure, had never heard of that function. But I will tell you that the inverse Ackermann function of n is less than 4 for every number you can possibly imagine. Yeah, so it's basically 4. Yeah.
Does this algorithm like ever fail?
No.
Like, it's always gonna find.
Yes. Yes. Yeah. Yes. So like I said, basically constant time, technically not constant time, but basically constant time. Cool. Oh, that's a great question. Does it work? I guess that's what we're going to cover next. I'm going to skip a little bit part of this, but it basically relies on our lemma from last time, where like for any cut, if we look at the lightest edge, it is okay to add that edge because that edge belongs to some minimal spanning tree. Okay, so this is doing exactly that, right? So every time we are considering, so this is our lemma, right? It's like, suppose you have some edges that you've already taken in. Suppose there is some cut that like respects the edges. So that means it's not going, none of the edges are going across the cut. Then if you consider the cheapest edge across that cut, it is possible to create an MST that has that edge, right? Therefore, that's the lemma that we talked about last lecture. Therefore, this algorithm, literally what it does is anytime you're considering merging these trees, you can say, well, here, this is the cut. Something crossing that 4 is the cut. And we're going to take the cheapest edge. Therefore, by our lemma, it will belong to an MST. Does that make sense to people? So like that's why it always works. It will always return an MST for you. So really, we're relying on the lemma. So if you assume the lemma, this should make sense to you, why the algorithm works. If you still don't understand the lemma, then you want to review last lecture and maybe think about it a little bit more. Cool. Okay. Oh, I meant to skip this slide. Yeah, we're going to skip it. Cool, cool, cool. So what's next? What have we learned? So this is what we've learned. This is a review so far. This is what we just learned in the last 30 minutes. Okay. Kruskal's algorithm greedily grows a forest. It finds the minimum spanning tree in m log n time. And again, the m log n actually comes primarily from the sorting. So if you can do sorting faster, your algorithm will be faster, right? And then to prove that it works, we follow the same recipe as before. Cool. So let's compare and contrast. This is Prim's and Kruskal's algorithms. So there are two algorithms. They do the same thing. They both find the minimal spanning tree. Prim grows a tree. It's always connected, and it always adds the edge that will grow the tree. It takes running time m log n. How did we know this had running time m log n? Because it's similar to Dijkstra. So again, this is what we mean. We're like, as you learn more stuff, you start building up on it. Okay. So if you're like, I don't know why Dijkstra has m log n running time, then you don't know why Prim has m log n running time. But if you remember Dijkstra and you remember why its running time is m log n, then you can say, well, Prim is the same algorithm, except our update rule is different. We just change, instead of like Dijkstra does, du plus the weight, right? Prim just says, look at the weight. That's the only difference. the algorithms are exactly the same otherwise, which is kind of interesting. But it also explains why Prim and Dijkstra were such good buddies. Okay, Kruskal grows a forest. Running time is again m log n if you use the union find data structure, but it's primarily dominated by the sorting of the edges. So if you can do sorting faster, Kruskal is faster. So Prim is probably a really good idea if you have really dense graphs, or if you cannot radix sort the weights. So if you don't know anything about the weights and you can't use radix sort, Prim might be a pretty good idea because its running time, its optimal running time is like n log n plus n, right? So if you have a really fat graph, this is going to be less than this. But Kruskal might be better if you have a graph that does not have a lot of edges, or if you can radix sort your edges. So like if you know the maximum weight of an edge is going to be 50 and you can bucket sort it, then maybe Kruskal is better. Okay. Here's a good question you guys should ask yourself. So it turns out both of these algorithms, it has not been proven. We do not know the optimal algorithm for this problem, find minimal spanning trees. The latest advancement, I was actually trying to read this paper because this is such an interesting running time. I'll give you guys like a second to read the running time of this algorithm. So to summarize, Karger, Klein, Tarjan. So this guy actually went to Harvard. He was an alum. I was very happy. Some of the other people went to MIT or whatever. They discovered a randomized algorithm that is actually O of M. Okay, it's actually a really simple algorithm. We're going to cover it in one of our future lectures. Somebody improved it to M times the inverse Ackermann function, which is basically O of M, and they made it deterministic, right? So this is like M times 4, okay, at most. But in theory, it is not O of M because this function does grow with N. It just grows really, really, really slowly. And then these guys came along in 2002. The paper is actually really interesting. I don't understand most of it, but they found an algorithm. They have an algorithm whose running time is how many ever times you need to compare edge weights for your graph. Whatever is the minimum number of times you need to compare them, that is how fast our algorithm runs. But they don't actually know how many times you need to compare the edges. So, and that's still an open research question as to whether you can do better than that. Cool. Okay, so again, just to summarize, this is what we've covered so far. Any questions so far? So Kruskal, if you guys are interested in trying to improve that algorithm, go for it because we don't know what the best one is. Cool. All right, next up, we're going to cover maximum flow. It's a slightly new topic. All right, so reset your brains. Be like, I have learned everything I need to know about minimal spanning trees. And this one actually has a really interesting history. So I'm going to have a lot of fun with this. Okay, this is the minimal flow statement. This is the problem statement. It's a more general problem statement. You are given a graph that is directed. So it's a directed graph that has weights on the edges. The weights we're going to call capacities. Okay, and that'll make sense in a second. You are also given two special nodes. You're given a node called S, which is the source. It has no edges going in. And you're given a source, a node T, which is the sink. It has no edges going out. Okay, this is part of the problem statement. This is what you're given. You're given a graph with weights, a node S and a node T. Okay. So these assumptions make the problem easier, but you don't need them because you can imagine you can always add a node. Like if you have several nodes that are sources, you can always add another node S that's a single source that feeds all the other nodes. But anyway. Okay. Now for this graph, we're going to define something called an ST cut. So an ST cut is a cut that separates S from T. Make sense? This is an ST cut, okay? Because S is on this side and T is on that side. Got it? An edge crosses the cut if it goes from the side that S is on to the side that T is on. Okay. So these three edges cross the cut. This one does not cross the cut because it's going from the T side to the S side. Okay. So again, these are definitions to help us understand this problem. Okay. Do you guys see why only these three edges cross this cut? They're the only ones going from the S to the T side. Okay. So you have an ST cut. Now you know edges that cross the cut. And the cost of our cut is the cost of the edges that cross the cut. Added up. Okay, so what is the cost of this cut? 16. 10 plus 4 plus 2. Okay. A minimum ST cut is a cut that separates S from T with minimum cost. Okay, so again, just definitions. You guys are introducing to the problem statement. Okay. This is not the minimum ST cut. Can you guys find another one that's smaller? There's one that's 11. But you know that. We're gonna find an algorithm in the next several lectures to find minimum ST cuts. Surprise, surprise. Turns out minimum ST cuts also define maximum flow. They're like two sides of the same problem. Okay. Now here's an example where this came up. So this was actually declassified in 1999. So I know a bunch of you guys are like, I feel like NCAT has like pretty close relations with the military. So I always wonder like what the government is up to nowadays. Like what's all the secret stuff they're doing. But it turns out back in World War II, this didn't get declassified until 1999. This is a map of, can you guys tell what this map is of? What region of the country or like of the world? So see the Baltic Sea. So this is in Europe, and it is a map of the railway system that the Soviet Union used to supply its different camps in Europe with resources, right? So it's a supply line map that they had captured. And this was in 1955. It was declassified in 1999. It has 44 edges and 105 vertices. So the vertices are where the resources are going. The edges are connections defining they can get resources from this point to this point. Okay. Turns out the US wanted to know what are the minimum number of railroads we can blow up to completely disconnect the supply chain that the Soviet Union had set up to supply Eastern Europe. So it's a pretty grim use of this algorithm, but you can imagine what actually happened. So this map itself, this is why this algorithm was invented, by the way. This is not even like they just used it for this. This is like they invented the algorithm to solve this problem. And now we use it for a bunch of other stuff, but like this is why it was invented. In 1955, Ford and Fulkerson, those are their names, gave an algorithm which finds the optimal ST cut. And you can actually, this is the map where he ran his algorithm on it. These numbers here on the edges are the capacities of that railway. So it has the edge weights. And there's a little dotted line that he drew here. And he calls it the bottleneck. Because this is the cut where if you blow up all of the railroads in that cross the cut, that is the minimum capacity. That's the minimum capacity you can destroy, but still disconnect the two sides. Okay. So is that cool or grim? Both. Okay, both. So yes, I like the answer because it's a Boolean, right? It's yes, right? Whether it's one or the other. But that is how this algorithm was invented. So I always wonder, I'm sure the government is up to some stuff now, and they're probably coming up with some algorithms that, we didn't know this until 1999. So we knew the algorithm because they published the paper, but we did not know this is the reason they were designing the algorithm. until the military declassified it in 1999.
You probably don't have to watch this now.
Oh, me? No. This is public. It's declassified. This is public knowledge. But again, this motivates you. So all the algorithms we learn, first of all, they do have practical applications. A lot of algorithms actually are developed first for some application. And then they become like, oh, it turns out we can use it for a bunch of other stuff. Let's teach it to all these undergrads so that they know it, you know? So let's continue. So we're going to define something called a flow. So this is going back to our graph. So I added these like little boxes, 4, 1, 2, 1, 1, 2, 2. Okay. So each edge is going to have a flow, which is like how many resources are going on that railway track. Okay. Obviously, the flow on an edge has to be less than the capacity, right? You can't fit more resources than you can fit, okay, along one railroad track, okay? At each vertex, the amount coming in has to equal the amount going out. So you'll notice from, except for S and T, because S is like the source, this is just the origination where everything is coming from. T is where everything is going into. But for every other node, you'll notice that if I have a flow of 4 going into here, 1, 1, 2, the amount going out has to equal the amount going in. And that's true for every single node that's not S and T, right? This is like a really practical problem. Like you should be imagining like oil pipelines between Russia and Ukraine. Okay. Anyway, actually, I would not be surprised. I mean, I'm sure people are thinking about that, right? But I'm not. But here's an algorithm. Here's an algorithm that would help you identify what are the pipelines you have to cut, you know, the ones with the least capacity, so that all of Europe no longer gets oil. Yeah. Cool. So that's what I was talking about. So 4 units going in equal the units going out. Why is this assumption, like, why might this particular assumption not be realistic in like the real world? Yeah. Yeah, you might have more than one sync node. It turns out it's actually pretty easy to fix by connecting all your sync nodes into one giant sync node that just have edges going to that. Another assumption is like in the real world, you might lose some resources along your network. In the real world, your capacities might not be fixed. You know, like if I really wanted to, maybe I could like, you know, like is 3 really the max? Or like if we really had to, I could get more going through that railroad, right? So again, a lot of computer science studies these algorithms. We like apply them to real world problems. So once you get to the real world problem, like there's a lot more complexities you have to consider. So that's called a flow. The value of a flow, so when I'm going to talk about the value of the flow, is going to be equal to the amount coming out of S, which is equal to the amount going into T, right? So how big a flow is equal to like how much I can push out of S, which is my one source node. Okay. So the value of this flow is 4 because I'm pushing 4 through here, through this edge. That's how much is coming out. Is this the best flow that you guys can imagine? Or if I'm Vladimir Putin, could I be like, you know, I think I can push more oil through this network? Huh? Yeah. How would you push more flow through the graph? Yeah, you've got like a 6 here, right? You got like push 6 here, and then I mean the 6 can go through the 10, and then I guess you can only maybe another 4. For sure, another 4. We could do another 4, right?
You can go to like the 10, and like go back.
Go to 10, then go back to 3, and then go to the 3 here.
Yeah. But
and then another 2 here.
Yeah.
Yeah. Okay. So what is the maximum you could get? What do you think? I hear 16. It's definitely not infinite. Definitely not, because at most, like stuff has to go into T. So at most, it's like 4, 4, 4, which is 12. At most, it's 12, because you cannot push more than 12 into T, right? There's no other way, right? And you also another way is like you can only push out at most 6 plus 4 plus 2, 12. You can also only push out 12. Right? So yes, I agree with you. There are cycles, but it does not let you push more through it, because once the cycle fills up, it is like it's now filled up, and it's not like the cycle doesn't help you move more from S to T, right? The goal is to move from S to T. Yeah. All right, so I'll let you guys think about that problem over the next couple of days. Maybe hit up some of your friends at the government, ask them if they are doing anything related to this, and tell them to hit me up so I can tell you guys about it. No, I'm kidding. Anyway, this is so the problem, and the reason we introduced these two problems together, there's a minimum ST cut problem, which is what is the value of the smallest cut that I can make in a graph, ST cut. And there is also a problem called the maximum flow problem, which is what is the maximum amount of stuff I can push from S to T. It turns out those two problems are the same. Okay, cool. Also, there's yeah, so we'll cover that next time. Thanks for coming. Thanks everybody on Zoom. I'm gonna stop recording and end the call. See you guys.